partial derivatives. Let's talk about this equation. 2y divided by x squared. Technically not an equation, an expression, right? If I give you an x value and I give you a y value, you'll plug both of those in, we get a number. Number pops out. Feel good on that? Right? So that means that we've got, like, it kind of looks a lot like our implicit equations. You remember those when we had all of our x's and y's all mixed in together? Right? They were implicit equations because we were implying that x connects to y. So for example, like this, right? Had a bunch of x's, y's mixed in, could do derivatives on it, no problem. It was an implicit equation because it suggests, it looks like we could solve for y, right? Like, doesn't it kind of feel like we could solve for y? Like, we obviously can't solve for y because there's too much else going on, but it looks like something where our initial gut reaction would be, oh, well, I'll just try to make this y equals. And that was our barrier. That was our original barrier, is I can't make this y equals, what do I do? This up here, though, this is a little bit different. There is no equals sign. So there's no implied connection between x and y. It's just, I give you an x value. I could also give you a y value. And any x value and any y value I give you will work with the thing on top. What about the one on the bottom? If I give you any x value and any y value, will that work for the equation on the bottom? Let's try. Let's try plugging in, I don't know, 200 for y and 1 for x. Is that going to work? Try it. 200 squared is going to be big, right? And then 3 times 1 times 200, we think all that's going to add up to 3? Paper, right? Plug in. What did I say? 200 for y and 1, x equals 1. Like, is that going to satisfy our lower equation? It's not going to work at all, right? So there are sometimes the lower one works. There are sometimes it doesn't. What about the one on the top? If I give you y equals 200 and x equals 1, will you get an answer? So we've got something that looks visually the same, but there's a difference. The bottom one is an equation where I imply a connection. The top one is just saying, I'm going to do some stuff. Okay. So that's the first thing that I just want us to recognize is, yes, it looks similar, but it is different. The one on the top doesn't have an equal sign. It doesn't require me to have a connection between x and y. I could honestly put any x and any y in the top, and so long as I don't create a divide by zero error, we're good to go. So how could we write this one up here? Well, if this works for any x and any y, except for a couple of one-offs, we can next ask ourselves, if I give you an x value and I give you a y value, how many answers will the calculator output? Like, let's say I did put x equals 1 and y equals 200. How many answers will the calculator give us when we do that? 1. What do we call a statement that gives us one answer every time we try to input stuff? A function. So that becomes our notation. We'll say that the top thing is a function, but it's not just a function of x. X is not the only thing I'm plugging into it. I'm also plugging in y. I plug in x and y. So we got a little new notation here. You can have functions of multiple variables because if I take those two numbers and I plug them in, I get one singular output. On top of that, is the thing that's coming out going to be equal to x? Equal to y? Something completely different. All right, let's try. Let's plug in. I'm seeing a couple of lost looks. So let's try the numbers I keep playing with. X equals 1. Y equals 200. If I plug these in, do I get x to pop out? Do I get y to come out? Or do I get something completely different? Something completely different, like a whole new thing, like a whole new output variable. So that's why sometimes people will refer to this as a new letter, z. A new number. But for our purposes, I mostly just want us to recognize that this is a function that behaves not in two-dimensional space, not in I plug in X, I get out Y, but in three-dimensional space. I plug in X, I plug in Y, I get out new number. Call that Z if you'd like. Call it F if you'd like. All fine for me. So we could write it like this. If I have X and I have Y, I can plug it into the structure. It will output a single number. We will call that a function. But that means that I've now got two things going in and one thing coming out. That means that I've got three different variables to keep track of. That means I'm talking not about a 2D graph, but a 3D graph. So it's going to look a little something like this red right here. This represents your X value. This green right here, this represents your Y value. So depending on where we are, if we go more X or more Y, less X, less Y, negative X, negative Y, doesn't matter. When we plug all that in, we will get a new number that comes out, and that new number that comes out will be the answer, the output, the Z value if you'd like. And so you get something that looks like this. So this is what it looks like to look at a three-dimensional equation. If y'all ever get the inclination, want to come take Calc 3 with me, we'll do a lot of stuff like this. Play with this all the time. Because in all honesty, this is the real world, right? Like the real world is three-dimensional. If you're ever going into, or if you know of anybody who's going into things like meteorology, right? You got to deal with, well, three different dimensions in space, right? Because you have your longitude, your latitude, and you also have your altitude, right? Three different spaces. And then you use all of those inputs to be able to figure out the weather patterns and such like that. When you're talking about economics, what are some different inputs that might affect the price of something? Taxes, materials. Sure, we can talk about rates of exchange, right? If we're talking across borders, labor costs, supplies, demands. So before you know it, you're playing with economics of 5 or 6 variable expressions. You're playing in a 5 or 6 dimensional space. But we don't have to have it actually look like we don't have to be able to draw it. We just have to understand, like, there's nothing to say that many, many, many different pieces of information are required for a given problem. Like that happens plenty. So our deal is just to take a look at this and to tie in a couple of different things that we can recognize about the calculus of it. Like, for example, its slope. Its slope is difficult to tell right here. Because slope where? Let's imagine that this is an actual piece of land and you are trying to climb it. You're trying to hike this object. What would be the best way to hike it? Do you want to hike right here? Do some vertical rock climbing? Does that feel pretty good? That'd be pretty steep, right? We could come over here. Here, it'd be a much more gradual incline, probably a better idea. If you come over here, it gets steeper. What about going this way? Going this way, it's not bad at all. So we've got a derivative, but a derivative that changes depending on how you are climbing. Your slope changes based on your direction of travel. Okay. So that's just the overall synopsis, just to get us comfortable with the idea of graphs that extend into 3D space. Thankfully, the calculations really aren't all that much. So I'm showing this as it's going to be like a lot of front end conversational, and then we're going to do the computational. The computational is pretty straightforward. So just like a real life surface, we can see there are places that are going to be steeper. There are going to be places that are shallower. So if I ask you for the derivative, sometimes the derivative will be high if we're talking about a steep place. It'll be low if we're talking about a shallow place. We're just trying to talk about this in terms of math. Now, the thing that we're going to limit ourselves to in this topic is we're going to limit ourselves to 2 different directions. What would be a good color? Pink. The first is, since X is coming out this way, we will talk about what happens if I am traveling in that direction. If you want a metaphor, think about this as east and west. So it'd be a matter of saying, how steep is my journey going to be as I travel from east to west? Well, if I follow one of these lines from east to west, you will see that that is the curve that we are talking about. That would be one journey from east to west. Here would be another journey. back here where you climb behind the mountain and then you pick up on the other side. That would be another east to west journey. What about north to south? I could travel north to south across this thing. And if I travel north to south, then all of a sudden I would be tracking along these lines. These are all north to south journeys. And what we do when we solve this is we're taking something that's three-dimensional and we're just looking at it through a certain lens, a very small bit to help get us an idea. But that's the picture happening behind the scenes. Anybody need any clarification on what I'm referring to when I'm talking about like this east to west, north to south, these slopes that I'm looking at as we traverse this terrain? Yeah.
I feel bad for the people coming from that side because they're just going to plunge into a black hole.
Oh yeah, there's a whole bunch of fun things you get to do when you create three-dimensional graphs. Like you do to do just, we don't even have time for me to describe how awesome three-dimensional calculus is. But for our purposes, we're going to limit it down to this. Couple of key questions that I just need us to be aware of. First questions first. If you travel in the x direction, think about that as east to west. My question to you is, does your y value change? Does your north-south?
No.
Right? If I travel east to west, does that affect my north-south at all? Not a bit, right? That's a nice takeaway. That's a nice way of recognizing it. What about if I wanted to talk about me traveling north-south? Is that going to affect my east-west? Not a bit, right? They'll both affect how high I go on the curve. That's fine. But I'm just talking about if I decide to talk about traveling in one direction and not the other direction, then that's a pretty simple discussion. I don't have to worry about there being overlap. In other words, there's no connection between X and Y in these storylines because they didn't start off as equations. They started off as formula expressions. So we're going to talk about these journeys and we're going to describe them as partials. Partial journeys are where I am only traveling in the X direction or I am only traveling in the Y direction. It's going to make our math much, much easier. If we want to talk about the derivatives, those would be the derivatives of the partials. We could define a certain track that we are going to walk along, whether it's east to west or north to south, and then we'll do a derivative in that direction. All right. Lots of preface. The calculation is a lot easier, I promise. We're going to come up with a new notation. The notation is f with a little subscript y. What this is going to mean, it's going to mean that I'm going to do the derivative, but it's a partial derivative where I am only looking at how I change y. So in that case, let's look at this story. I have 2y over x squared. But that was the original function. I now want to know how it changes based on y. What's a way of writing looking for how it changes based on y? Not dy dx, that would be how y changes based on x. d dy, right? I want to find the derivative of this thing with respect to y. Now, again, this is where if we look at it for our symbols, you're going to get very confused with your implicit differentiation because our implicit differentiation started with a storyline where y and x are connected by an equal sign. Here, I have no y and x connected by an equal sign, and I'm still trying to figure out how things change. So let's ask ourselves, how does the y component of this, I got 2y on the top, how does 2y change? What's its derivative? 2. How does x squared change in this story as you change y? It doesn't. Traveling north-south does not affect your east-west. All right, and that's the storyline we're starting with. So that derivative then of the x squared would be, I'll just stick around. Now it's a little bit informal. If you want me to write this a little bit more formally, here's how we can think about it. 2 over x squared in this storyline, this whole thing, we're going to treat it as a constant. Why? Because x isn't going to change as I travel in the opposite direction. East-west doesn't change as I travel north-south. So when we did its derivative, we did the derivative of this. Well, you all tell me, what is the derivative of number times y if I'm trying to do a derivative based on y? So in other words, what is the derivative of number times y?
The number.
Just the number. And that's how we get to being just the constant. So this would be the formal way.
So I look at this and I notice that if you did multiply y into the constant,
Mhm.
then it would be 2y over x squared.
Sure. Yeah, that's where we started.
So they're the same thing. That's cool.
Oh yeah, for this one here. Yep, this is us just looking at it as saying which of these things are being constant in the story. In this particular story, numbers of course don't change, but also x is not changing because I'm not talking about traveling in that direction.
So say like it was flipped, like x squared was on top and 2y was on the bottom, but the notation said fy.
Mhm.
Would you still only?
Ah, good question. Okay, so we'll do a little parallel problem down here. So you're trying to say let f of xy equal x squared over 2y like this, right?
Yes.
Okay, then the first thing we could do is we could try to expand this so that we have the stuff that's not changing and then the stuff that is changing, right? What we would not want to do is say that this is the same thing as that. That's definitely not true, right? What correction would I need to make? Yeah.
1 over y.
1 over y. There we go. That's a lot better, right? Much, much better. And now if I wanted to do its derivative, this is a constant. What's the derivative of 1 over y? Not ln. You're thinking integral. It may help if we first rewrite this in terms of it being a power, since we've been playing with powers quite a bit. Y to the negative first. And then what's the derivative? How do I do a derivative with power rule? Number comes to the front and I multiply by it, decrease the power. So then this entire thing becomes negative x squared over 2 times y to the negative second. Right. Same exact rules. The importance is that we just got a slightly different storyline. Nothing too crazy, thankfully. All right, let's do this one now. F with a little sub x. We got enough time, so why don't you on your end try that out. I'll give you a couple minutes and then we'll compare answers. So remember that it's the derivative based on x. But in this storyline, we are pretending that, or not pretending, but we are acknowledging that y does not change based on x. So give that a shot. All right, so in this situation, we're looking for as I change x. As you change x means as I am traversing along the direction of x, along the east-west direction. So when we do this, we've got 2y, which is going to be constant. Treat it as constant here. And then how do I write that x piece? I can make it 1 over x squared. As we do the derivative here, maybe we first rewrite it in terms of power. We got 2y times x to the negative second. Still haven't done the derivative yet. This is me just algebraically manipulating it. And then how do we do the derivative of that constant times x to the negative second? Power comes down, decrease it by 1, right? So it would be power comes down, making it negative 4y. Decrease the power by 1 gets us x to the negative third. So what is this thing? Like what is this thing? This is an equation that describes your slope along your journey east to west, depending on your x and y value. So in other words, maybe my x and y value is here. That looks like an x and y value. Well, east to west would be here. And so your slope would be the slope of that tangent line. It'd be how quickly you are traversing slope-wise as you travel x directionally of this big three-dimensional terrain.